Hi, everyone. My name is Ray Zhang. I'm a field application engineer specializing in wide bandgap devices at Richardson IPD. Today, we have Silicon Carbide power MOSFET expert, Adam Enders. He's the manager of power platforms at Wolfspeed. He's going to go over some details about the double pulse test regarding to the Silicon Carbide MOSFETs. Hi, Adam.
Hi.
First questions that comes to my mind when we talk about the double pulse testing. So what is the significance of this double pulse test and why do we need it?
Yeah, that's a great question, Ray. Double pulse test is really a fundamental test that's performed on power switching devices, MOSFETs, IGBTs, anything like that.
Right.
And the reason for the test is to really understand the switching energy and the switching behavior of the device. And so to perform this test, you have a half bridge arrangement of, in this case, silicon carbide MOSFETs or a silicon carbide MOSFET and a diode. And what you can do is ramp up the current to a certain level and turn the device off and back on and make measurements at those current levels. So you can see how the device switches off, how it switches on, look at things like rise time, fall time, and then it also gives you an opportunity to optimize your gate drive circuit. So if we look at the waveform here, this just shows how the current behaves during the test. So during the first part, you turn
Mhm.
on that lower MOSFET and it ramps up the current, and then you turn it off. And during that off time, current freewheels through the inductor and the upper body diode or Schottky diode, whatever you have in place there. And so at that turn off event, you can zoom in on that part of the waveform and make measurements at turn off. And then you can turn that lower device back on again, and the current will be very close to where it was left off because it was just circulating through the inductor during the off time. And so you can then measure a turn on event with that amount of current in the switch. And doing this allows you can run this test at different current levels. You can run it with different gate resistances, different bus voltages. So it really allows you to build up a good understanding of how the device switches across a wide range of operating conditions. So just looking at the waveforms here, when it comes to making those energy measurements, you can see the two main things we need to measure is the voltage across the lower switch and the current through that switch. And so looking at the top plot here, as that lower switch turns on, you can see the voltage ramps down and the current is ramping up. And so multiplying the voltage and the current during that switching event gives you a power, and then integrating that power over the entire time of that switching event gives you the turn on energy. Likewise, on the turn off, voltage comes up, current comes down, and you can do very much the same thing there. Multiply those two waveforms to get power, and then take a look at the energy by integrating it.
Yeah, I see the switching waveforms. That's how you calculate the energy dissipation during the switching event. So, Adam, one challenge I think is particular big challenge for the silicon carbide is the high switching speed of such device. And when you perform a measurement in circuit, how do you accurately capture the current and the voltage given the consideration of such high switching speed and also the common mode noise?
Absolutely, yeah. That's one of the fundamental benefits of silicon carbide is its quick switching times. That's what helps keep the switching energy very low. However, those fast DVDTs and DIDTs make it challenging to make accurate measurements. So we've got some tips to help you be more successful at making these measurements. In regards to the voltage sensing, if you've tested with IGBTs or you're familiar with those in the past, you could get away with being fairly sloppy on your probing techniques because the rise times were relatively slow. If you try to do the same thing with silicon carbide, you're going to end up seeing things that are not real, and it can look really scary. We have an example here using a standard 10-to-1 scope probe with a regular ground clip on it to probe the gate voltage, and you can see that waveform is in the blue here. So if you saw that, you'd be pretty concerned that your gate is overvoltaging and ringing a lot. But what's actually happening here is the probe itself is picking up noise, and it can ring with the circuit as well from the inductance in the probe and the capacitance in the probe. So what we recommend is using a probe tip adapter or some sort of a coaxial connector like an MMCX or SMA, BNC, any of those types of coaxial connectors to make that connection between the probe and the point that you're trying to read on the board. And so that's what you can see in the yellow waveform here. We went to a tip adapter that has a very small loop area between the tip and the ground lead,
Mhm.
a very short loop there, and that really
Right.
cleans up the signal. So this is the same signal, just with two different probing techniques, and that makes all the difference in the world. So similarly, when you're probing the drain voltage during a double pulse test, you have the same considerations there. You need to be cognizant of the probes that you're using, the parasitics that you're introducing in the circuit, and any pickup that you might be getting from those as well. Likewise, the current sensing can actually be the most difficult thing to measure. So we've tried lots of different techniques to understand what current sensors would work best with silicon carbide. And really, the Rogowski coil is not well suited towards it. Current viewing resistors can work, but they do introduce a little bit of overshoot in the current signal with very high DIDT parts. So the two solutions we found that work the best are a two-stage current transformer or small surface mount shunt resistors, a large bank of paralleled surface mount resistors, and then a nice coaxial connection very close to those for performing the sensing.
Yeah, thanks for sharing the tip about measurement. Yeah, we know that any little loop inductance in the probe setup will cause a big noise issue. And also, in order to make these energy loss measurements, you need to multiply and then integrate the voltage and current waveforms. However, you're using different probes to measure the voltage and current. Does the difference in the response or delay time of these probes really gonna matter, affect your results?
Yes, definitely. That can actually have a very significant effect. So what we do is a process called DeQueueing. Scopes have this built into it where you can shift traces relative to each other in time. And it's incredibly important with silicon carbide to do that. When you're using different probes, you can have variations anywhere from a couple nanoseconds to tens of nanoseconds. And while that might not be much in a lot of contexts, with silicon carbide, if the entire switching event is 20 nanoseconds, being off by a few nanoseconds can actually result in a large difference in the switching energy. We could be talking a 2x difference if you don't deskew the probes properly. So the procedure that we follow to deskew the probes is to basically take that half-bridge circuit and put a resistor, a low inductance resistor, across the top device, and then gate the bottom device on so that you get just a nice square wave of current flowing in the circuit. And ideally, if it's a nearly purely resistive circuit, the voltage and current should be in phase with each other. And so then we can take those two voltage and current waveforms and time align the edges. So you can see that in the images here on the bottom. The one on the left is showing the initial condition without applying any deskew to the probes. The voltage and the current signals are misaligned there. And by applying, in this case, 1.92 nanoseconds of deskew, we were able to time align those so that they line up nearly perfectly there. Now we're all set to take that resistor out and start doing the double pulse measurements and getting accurate time aligned voltage and current signals out of it.
Got you. Yeah, it sounds like it's certainly a very important test to perform on the silicon carbide device. However, due to the high-speed nature of the device, it's very challenging to capture all the data correctly. So I was wondering does Wolfspeed provide any kits or evaluation tools in order to make this test easier for the engineers?
We do. In fact, we put significant effort and resources into developing evaluation boards for our customers to make these measurements. So you can see here we've got a variety of different boards for doing double pulse on our modules. So there's different boards optimized for each of the different module footprints. And then we've got an exciting new platform coming out called the SpeedVal kit. And that is a modular kit designed for our discrete devices. So you can actually test out different gate drivers, MOSFETs in different packages, different RDS(on) MOSFETs, all by just plugging and unplugging boards very quickly. And so this board was set up using all the features that I just talked about, coaxial connections for voltage sensing, surface mount current sensor, also the provision for the two-stage CT that I mentioned. So this board can really make life easy for getting double pulse measurements accurately.
I see. So does the motherboard is the same for different kinds of devices that's plugged into the daughter card, right?
Correct. Yeah, the system's very flexible, so that same motherboard can be used for 650 volt or 1200 volt MOSFETs in surface mount and through hole packages. So it's very flexible, covers kind of that whole discrete portfolio up to 1200 volts.
Yeah, that would really make engineers' job a lot easier. Adam, thank you so much for sharing the tips about the double pulse test on silicon carbide devices. And we also like to thank our audience for participating in today's event. If you have any questions, feel free to reach out to our FAE team at Richardson IPD and also Wolfspeed support team. Thank you very much.
Thank you.